I got a picture of a guy sawing a log and a box of Wheaties. And the question, yes or no, and the question is, will the guy that's cutting the log need any Wheaties to do that job? In other words, if he's going to put out energy and his body's going to start radiating heat and his blood rate and pressure, heart rate and blood pressure are going to go up, that energy has to come from somewhere. Where is that energy coming from? Well, it comes from the Wheaties that he eats, right?
Yep.
Simplifying things. Now, here's the question though. If this guy moves the saw 24 inches in one direction and then moves it 24 inches back, after doing that for even an hour, there's been no change in position. You agree with that? In other words, if I do this and put it right back where it was, after that amount of time, there's no change. Nothing has changed. So if you think about it that way, if he's moving 24 inches in one direction, the 24 inches in the other direction undoes that 24 inches, right? Doesn't it? So therefore, he shouldn't need any Wheaties. Because for every 24 inches he moved it in one direction, he basically rescinded that when he pulled the saw back in the other direction. So the net gain is 0, isn't it? So he shouldn't need any calories to do that. In other words, he should be able to do that until hell freezes over without getting hungry. But we all know that's not the case, don't we? It's not really how it is. What's true is that a change in direction implies still constant work. And another way, in terms of electronics, that we can look at that is that power is always positive. Okay, in other words, there's really no such thing as negative wattage.
We joke about there actually is in a sense, and that's when people with solar power sell the power back to the power company, and they consider it to be negative because they're getting power back, which is not a normal situation. So for them, it's a negative.
Well, yes, and on a balance sheet, the money that I spend every month is negative dollars.
So for them, power is negative as it comes back.
Yeah, but it's really not. That's just
Yeah.
on a balance sheet. It's still power.
Yeah.
It's still positive power. From my perspective, sending it back, it's positive. I'm making power. So it all depends on direction, and that's really what the point is that even if you have a change in direction, you still have a constant amount of work. The power is still the same whether it's moving in one direction or the other. So the answer here is yes, he will need to eat his Wheaties because even when he's moving the saw backwards, he's still expending energy to do that. Okay, now we need to come up with a way to represent that. Because clearly, from what we've learned about electricity, we should be pretty familiar right now with the scenario where we have a voltage that looks like this. That represents current flowing in one direction and then current flowing in another direction. And since for every positive value, there's an equal and opposite negative value, we could say that the overall result is equal to 0. In other words, if we took this whole thing part and parcel, moved it over here, there would be an opposing point. For every plus V, you'd have a minus V. If you add it all together, you end up with a flat line or 0. But with the previous example, we just proved that that's not really the way it works. So, here's what we have to do. Let's simplify things a little bit, and instead of starting out with a sine wave, we'll start out with a square wave. And our square wave will go like this. And let's say this is equal to plus 2, this is equal to minus 2. Somehow, I need to be able to represent these negative voltages as positive energy. These are already positive. Okay? How can I do that? If I want to make or force a negative number to be positive, how am I going to do it? Okay, so I have negative 2. And what I want to do is, like you said, take the absolute value of negative 2 and turn it into 2. Do you understand what absolute value is, Dawn?
I do.
Do you know what absolute value is? Okay, let's talk about absolute value. I am right now facing, which direction am I facing? Basically east right now. How far is it to Washington, D.C. from here?
Oh, about 3,000 miles.
So I'm 3,000 miles from Washington, D.C., right? How far am I from Washington, D.C. now?
3,000 miles.
No, I'm not.
Oh.
I'm negative 3,000 miles because I have to walk backwards now to get to Washington, D.C., right? Granted, funny story, but nonetheless, we don't represent distances as negative because really, if somebody asks you that question, what should your answer be? What direction are you facing?
You're obviously going to go the long route.
Right? Because I don't have the ability to turn around. I'm an electron. I'm just a stupid electron. I don't have the ability to make that decision. I'm going in that path because that's where I'm going.
Okay.
Maybe there's a wall that I can't go that way. Okay? That's the direction I'm facing. That's why we always look at something like this. All we're concerned about is the amplitude or the magnitude of the number. That's what we mean when we talk about absolute value. So how do I get the absolute value of any number out there?
Just put the little brackets on it.
That doesn't work. That doesn't work. Well, here's a thought. If I take the number minus 2, and I take that number and square it, what does that give me? 4.
Double it?
And if I take that then and take the square root of that whole thing, then I'm going to be left with the square root of 4, which is equal to 2.
Can't just use the brackets, huh?
Can't just use the brackets.
Got to do it the long way.
Got to come out with the number. Because this is a simple example. We're going to get ourselves into a little bit more difficult example here in a minute. But I use the square wave as a really simple example of how this works. So what did we do? What 2 functions did we perform?
Square and square roots.
We did this first. We squared. And then we did this. And we took the root. Okay? And as a result, that now means that all of these now turns into a flat line, +2, +2, because that doesn't change either, because plus or minus 2 will give you the same answer. +2, +2. So now we see it all as a positive number. Isn't that nice? Does that make sense, Dawn? Simple? Simple? All right, let's sweeten the pot a little bit. Let's make it a little tougher. Okay, I want to write down those two words. First thing we did was square, then we took a root it shortly thereafter. And that was the process that we used, because we're going to need that to do the next problem. Okay, in this example, we're going to change things up a little bit. We're going to label our axis, and we're going to call it the time axis, and we're going to mark this down in seconds. 8 seconds. And we're going to put down some voltages. 0, 1, 2, 3, -1, -2, -3. And here's what our voltage waveform looks like. I'll make that a little bit thicker for everybody. Now, when we look at this, we see that this is at 2 volts for 1 second, -1 volt for 2 seconds, 1 volt for a second, -2 volts for 2 seconds, and +2 volts for 1 second, and then 0 volts for a second. And what we would like to know is, what is the average amount of voltage over time? Remembering that negative voltages are just as important as positive voltages and represent positive power. The first thing that we need to do is make everything positive. Okay? So let's write down in green above each one of these what the voltage squared is. Okay? That's the first thing we'll do, is our squaring. 2 squared is 4. -1 squared is 1. -1 squared is 1, because we have to look at each increment. +1 squared is, -2 squared is, and +2 squared is. I actually have 2 4s there. +2 squared is 4, and then 0 squared, of course, is 0. Okay, so basically what I have is this. Let me draw this in, see if I can get purple to work today. This goes up, let's write down 4, because now all of a sudden we need 4. It's going to look like this. 4, 1, 1, 1, 1, 3 4s, and down to 0. And as soon as you're ready, we'll move on to the next step in this process. The first step was to square everything. But unlike the other example that we did, these numbers are different. And since what I said was we're looking for an average over time, what we're going to do is we're going to determine the average of these numbers. And that's going to be 4 plus 1 plus 1 plus 1 plus 4 plus 4 plus 4 plus 0 divided by, how many do we have? 8. Or 4, 5, 6, 7. 7 and 12 is 19 divided by 8. We all know, I assume we all know how to take an average. 19 divided by 8 is 2.375. Okay? Because we didn't have the same value through the whole thing. It wasn't a square wave. We now have to put in a second step, which is what we're going to call average or mean. Mean is just another word for average. Maybe whoever taught somebody how average was a mean teacher. I don't know why they came up with that idea, but whatever. So we did another step in that we took all of these numbers after we squared each one. We took the average, which means we added them all together and divided by the number of seconds. In other words, added up all these numbers, got 19, and then divided it by the number of vertical pieces, which is 8. Gave us 2.375. The square root of 2.375 will take care of the third part. And we can calculate that. Smart people like me still have the number in their calculator from the last conversation. And it's about 1.54 volts. And what that then means is that over a period of time, this funky waveform would basically be the same as having 1.54 volts all the time. Okay, so what we've done is we've taken a certain amount of energy and we have smoothed it out. We've smoothed out this irregular energy delivery and given us a number that is we can consider to be consistent over a period of time. So over an hour's worth of time or over a month's worth of time, and you may be familiar with this, Dawn, these silly looking outlets on our wall are guaranteed to put out 120 volts. That doesn't mean that at any instant it's going to be 120 volts. As a matter of fact, we know that when we look at what comes out of the wall, that it looks like this. Okay? That's what that looks like. If I do the same treatment to this, square everything, flip it up, take the average, I'm going to end up with something that looks like that. I'm going to take the square root of that, or the average of that, and then take the square root of that and end up with some value. And then when I take the square root of it, so this represents the square, this represents the average, and this represents the root. And when we do that, for our output of our wall outlet, this is going to be 120 volts. And we will refer to that as 120 volts, RMS, which stands for what?
Root mean square.
Root mean square.
Huh.
Okay, so that's where RMS comes from, is that is the process that we use to normalize this changing voltage to a total amount of energy over a period of time. Okay? In other words, what would happen is if this were cement, when we smooth out the ripples in the cement, that's when we find out actually how tall the platform is. Okay? And when we do this, we end up looking at 3 different numbers to represent this waveform. Okay? Remember, the blue waveform is the actual truth of the matter. Right here. And I'm going to eliminate some of this. Our RMS value is 120 volts. Our peak value is 170 volts. And our peak-to-peak value, bottom to top, is 340 volts. And we talked about what peak and peak-to-peak were last quarter when we originally looked at AC. But we didn't really talk about RMS. So here's the equations you need to be familiar with. And of course, voltage peak to peak is equal to 2 times peak voltage. And this only applies, and this is very, very important, that this is only applies to sine waves. These numbers only apply to sine waves, and those are really the only ones we usually care about, since that's what our AC looks like. Most of our AC is sinusoidal. That may not be the case when we decide to start talking about signals that carry information, but we don't use RMS to represent those signal strengths anyway. Okay? What this means to you as a technician is very simple. And that is, if you are going to do RMS measurements and you want to count on them, and I think, Dawn, I think we talked about this last quarter, you have to use a scope. You have to verify that the waveform is sinusoidal. If it's not, then that .707 calculation that you do is going to not give you the right answer. Now, for the most part, if we're looking at what comes out of the wall, for the most part, we can assume that that is sinusoidal because by law, it has to be sinusoidal. By law, it has to be 120 volts plus or minus a tolerance over a 24-hour period. So that does not mean at 9:29 it will be 120 volts. It might be 130, might be 112, but it'll be within a range and it will average out to 120 volts. Okay? That is what RMS is about. The importance of RMS to us is that it gives us an idea of the consistent power delivery. Okay? The waveform varies over time. Any questions on what we mean by RMS, why we use it, and what it is?
So, because it's been a long time for me, I know. So if I hit the RMS button on my meter, is it giving me the right number, assuming that of course we have a sine wave and everything? Because when we did this scope exercise last quarter, we realized how far off a meter gets from what a scope measurement would give you.
Yes, and that has nothing to do with the RMS aspect of it. What that has to do with is with the frequency responses. Think of it this way. Imagine a flashing light. Okay? I start to increase the rate at which that light flashes. What will happen as you watch it?
Probably a seizure.
Well, you might. Let's hope not. Let's hope not. But what happens is, at some point, usually about 24 hertz or so, you will perceive that light as being on all the time. Right? So there comes a point there. And that's, you know, that's kind of what this is about. It's not on all the time, but your eyes perceive it as being on all the time. This isn't on all the time either, but this is 60 times a second. So we need to assess or be able to determine what is the overall power delivery over time. That's what's really important. So that's why we use RMS. Plus, meters generally have a hard time responding that quickly to an input. Okay? Meters really can only read over time.
Because I mean, they all, you know, nowadays they almost all say RMS or have an RMS button.
Sure.
But it's.
But the question is, how high a frequency can it recognize before it just sees it as being on all the time? If it doesn't see these little valleys in between, it's not going to be able to recognize that. So normally, in the spec for the meter, it'll say AC measurements are good up to a certain frequency or a certain voltage at such and such a condition. So you always have to, that's why you should always keep the manual for all that stuff around. So that you have a manual tells you what the limitations of the equipment are. And if you try to use the equipment outside of its limitations, well, you know, that's your problem, and it's usually not a good one to have.